In topic 8, we're going to be looking at logarithmic and exponential functions. Now, up until now, we've been working with polynomial functions and rational functions, a rational function being the ratio of two polynomials. In this topic, as I said, we will be working with logarithmic and exponential functions, and these functions have important applications in economics, particularly with regard to growth problems. In topic 8, we will be looking at optimization problems where the choice variable is time. For example, if you have a piece of art that increases in value over time, the question you would like answered is how long should you keep that piece of art before selling it? So you will want to identify the time at which to sell. And to answer this question, we need to understand exponential and logarithmic functions, and we need to know how to calculate their derivatives. So starting with exponential functions, all the functions we've examined so far have taken this form here. For example, y equals x to the power of a. So we have a variable x, which is raised by some constant exponent value, for example, a. So we would have seen things like x squared or x to the power of 6. What we do now is we reverse the position of the constant and the variable. So instead of y equals x to the power of a, we will have something like this: y equals a to the power of x. So the constant is the base, a here would be the base, and it is raised to the power of the variable. So the variable now appears in the exponent. All right, and then we have these restrictions where a is greater than 0 and a is not equal to 0. And we know that when x equals 0, anything raised to the power of 0 will make y equal to 1. Okay, so just to summarize, an exponential function is a function whose independent variable, so that would be x, appears in the role of an exponent. Okay. Now, the value of x can be any real number. So it can be greater than negative infinity and less than positive infinity. And when we have these restrictions on the value of a and the value of x, what we will see is y is always going to be positive. It's always going to be greater than 0. And when we look at the graphs on the next slide, what we'll see is that if the base is greater than 1, then the exponent function is increasing and convex. And if the base a is less than 1, then the exponent function is decreasing and convex. Here we have two exponential functions illustrated, and the only difference between these two functions is the value of the base. So here, the value of the base is 3, so it's greater than 1. And here, the value of the base is 1/3, so it's less than 1, but obviously greater than 0. And what we are showing on this slide is what we've summarized at the top here. If the base a is greater than 1, then the exponent function is increasing and convex. It's increasing and convex. If the base a is less than 1, then the exponent function is decreasing and convex. And that's what we have illustrated here. Okay, and also what is shown for each graph is certain data points. So for example here, the exponential function is y equals 3 to the power of x, and we've just shown different values of x. And if you plug these values into this function, so 3 to the power of negative 3, you would get a value of 0.037, okay, etc. And these data points have been indicated on this graph, and here we have done the same. All right, so here the exponential function is y equals 1/3 to the power of x, and for different values of x, we will obviously get different values of y. All right, so there are a couple of points we want to highlight looking at these two graphs, okay, other than the difference in the value of the base. What we can also see is for both of these graphs, the y values are positive, okay? So the y values are positive here, and the y values are positive here. And that's what we will see for our exponential, the graphs of our exponential functions. We say more formally that the range, okay, the y values, the range is all positive real numbers. And then the domain, which is the x values, okay, and if we just look at these two graphs here, we can see that the domain is all real numbers, positive and negative. Okay, we can see that there are both positive x values and negative x values, okay, for both of these graphs here. The other thing to note about our exponential functions when we look at their graphs is that they are smooth and continuous, which tells us that we should be able to differentiate at every point. In other words, we can calculate the slope at every point along these graphs.